Hey guys, this is Yoru. In the last lecture, we have derived 17 equations to solve 17 unknowns for the dynamic analysis of the slider clamp mechanism. The 17 unknowns are shown here, and for the 17 equations, 9 of them are from Newton's equations of motion, or equivalently, nq double dot equals to sigma f, where m is the diagonal matrix consists of mass and moment of inertia of all rigid bodies. The q double dot is the unknown acceleration, and sigma f is the vector consists of all forces. As for the rest of the equations, they are from kinematic constraint equations, which are shown here, or equivalently, jq double dot equals to gamma, where J is the Jacobi matrix shown here and gamma is the vector shown here. So now if we want to solve for the Q double dot and the joint reactant forces using computers, we need to rewrite the equations in matrix and vector form, which is shown here. However, if you do so, you will realize you can't solve it since there are 8 unknown joint reactant forces in sigma f. So how can we solve this problem? Before we solve this problem, let's first talk about constraint force. So what is constraint force? Let's look at the slider here, which is translating on the ground and pushed by an external force, F. If we take the free body diagram, there will be a gravitational force mg, a normal force n, and the external force F acting on the slider. According to Newton's equation of motion, we can obtain these two equations. And since the slider can only move horizontally, we know that y double dot must always be 0. With these equations, we can solve for x double dot, y double dot, and n. Actually, for this example, we can think in another way. Since the slider can only move horizontally, we know that y double dot equals to 0. However, the force F applied on the slider is arbitrary, so the resultant force in y direction might not be 0. Therefore, we need a constraint force to cancel all the forces acting on the slider in y direction so that the slider can move horizontally. In fact, the constraint force here is the normal force n. Therefore, we know that the resultant force sigma f can be divided into two parts. One is external applied force, which is arbitrary, and the other is constraint force, which is restricted to kinematic constraint. So the motion equations can be rewritten as mq double dot equals to F applied plus F constraint. Now you might wonder, how can this be helpful? Actually, according to the Amber's principle, there exists a Lagrange multiplier lambda such that F constraint equals to Jacobian transpose times lambda. Therefore, the original motion equation can be rewritten as this, or this. Now we are able to rewrite 17 equations as this. Next, I'm going to use an example to show you that this conclusion is correct. Let's look at the pure rolling disk example. If we take the free body diagram of the system, we can derive these three motion equations, where I is the moment of inertia of the disk. Also, since the motion of the disk is pure rolling at high r, therefore, we will have these two geometric constraint equations. With these 5 equations, we can solve for 5 unknowns. The algebraic solutions are shown here. Or, if we apply the matrix and vector form conclusion we obtained just now, we will have the equations shown here, where the n, j, and f applied are shown here. Here, the Jacobi matrix J can be derived from two geometric constraint equations. And we solve for q double dot and lambda. We will obtain the results shown here. And we can get the constraint forces from J transpose times lambda. You will realize that the constraint forces we obtain here is exactly the same as the friction force F and normal force N we solved just now. So now I have shown you the matrix and vector form conclusion is correct. And in fact, we can conclude that the J transpose is the direction and lambda is the magnitude of the constraint force. Note that only when J transpose and lambda times together can we obtain the constraint force. Lambda itself is not exactly the same as constraint force. Here is a simple picture to illustrate the idea. The J transpose is the direction, lambda is the magnitude, and J transpose times lambda is the constraint force, which is the normal force N here. Now back to the slider crank example. We can rewrite the equations in matrix and vector form like this, where the matrix M, Q double dot, lambda, and F apply are shown here, and J matrix and gamma vector are shown here. With these matrices, we can use MATLAB to solve for Q double dot and lambda. In this case, after lambda is solved, the constraint forces can be obtained by this, where the magnitude of the joint reactant forces Fo, Fb, Fc, and N can be obtained by these equations. The reason why the magnitude of the joint reactant forces matters is because it is crucial when choosing the materials for the mechanism. So this is the end of this lecture. In the next video, we will show you how to do the dynamic analysis using MATLAB. See you next time.